All right, I guess I'll act as my own chairman and commence the final lecture of the week. So this is my last lecture. What am I going to talk about? So we've talked about, so far, supersymmetric quantum mechanics, how to make models with supersymmetry using superspace. And we've talked about the basic particle representations of supersymmetry in 4 dimensions, some aspects of supercurrents. And now we're going to talk a little bit about actual interacting Lagrangians in 4 dimensions with n equals 1 supersymmetry, and what kind of questions we want to ask about them and what can we say about them using supersymmetry. So this is the basic subject: Lagrangians, moduli, and non-renormalization theorems. These will hopefully be the highlight. And this subject sometimes goes under the alternative title, The Power of Holomorphy, after a famous paper by Nadi Seiberg. Okay. So what is the basic problem we're going to concern ourselves with? In 4D n equals 1. So we will have some UV theory, and it will have some vectors associated to some gauge group, plus some chirals, so vector multiplets and chiral multiplets, that are charged under this gauge group. So this will be something like a supersymmetric version of QCD. And we'll typically be interested in asymptotically free versions of that, so like a super version of the real world. And we'll just try and figure out what happens under RG at long distances. So what is the long distance limit of these kind of theories? Now, we've talked a lot about supersymmetric ground states, and let me make a crucial observation that relates to this problem and supersymmetric ground states. So we've seen that SUSY theories, or we will see, I should say, so SUSY theories can have moduli spaces. I'll call them M, of supersymmetric vacua. So in a classical approximation, we'll think of this as, so I'll put CL, think of what it is classically, as some space of inequivalent scalar vevs The scalars all reside in chiral multiplets because the vector multiplet doesn't have any scalars. And we're going to restrict to the locus where the potential V vanishes. That's because we want supersymmetric ground states. So remember, the potential is positive definite, and supersymmetry enforces exactly zero energy. Now, if you have a moduli space of supersymmetric vacua, then you can answer this question. Because the low energy theory will be a sigma model a nonlinear sigma model with target M. So why is that? Well, you think about it. So this is the space. Every point in this manifold, or this space, I should say, corresponds to some quantum state of exactly zero energy. And at low energies, you stay in that space and fluctuate very slowly. So you have a theory with target space M. So finding M essentially solves this problem. Supersymmetry will help with this. So SUSY implies several things. So the fields parametrizing M are chiral. They will be chiral fields. I'll show you some example to get familiar with this soon. And because of this, we'll learn that immediately M is Kähler. So in particular, it's a complex manifold, and it has a metric. And using supersymmetry, one can often find M as a complex manifold. As a complex space. You'll see why I'm resisting the word manifold momentarily. So with just n equals 1, it's typically impossible to figure out what the metric is. If n is greater than 1, can often find the metric also. So that's the big picture. If you have some ultraviolet theory, which is some kind of gauge theory, you want to know what happens at long distances. If you find this space as a complex manifold with its metric, then you could think of the infrared theory as a sigma model with target space, this Kähler manifold. And we can get part of the way there with n equals 1 supersymmetry, and with n greater than 1, we can usually get all the way there. Okay, so let's start now. Let's start with some theories of chiral multiplets. So these can be written in 4D n equals 1 superspace. You could think of this as an uplift to include the spin labels of the n equals 4 quantum mechanics superspace that we wrote before. So I won't be very explicit about it, but everything should be kind of clear. So in particular, a chiral multiplet is embedded inside a chiral superfield. Capital phi, and to say that it's chiral means that d bar alpha dot on phi is equal to 0. So all the superspace covariant derivatives annihilate phi. Okay, so we learned how to write Lagrangians for these kind of theories. We have two terms. One is the Kähler potential, and one is the superpotential. The Kähler potential is a general function of the chiral fields, real valued, and the superpotential is a general holomorphic function of the chiral fields. Now, typically, we want to start in the ultraviolet with a renormalizable QFT. So let's do that. Okay. So what should I choose K to be if I want a renormalizable QFT? So to get canonical kinetic terms, we need K of phi bar to be just phi bar I summed on I. So I'm imagining here I have some number of chiral fields. This leads to canonical kinetic terms. You remember we worked that out in our quantum mechanics example. Okay. What should the superpotential be if I want a renormalizable theory in 4 dimensions? How can I constrain it? At most cubic. Why is that? Right, so we should remember that the potential, so let's first write the answer. So W of phi should be some ai phi I plus bij phi I phi j plus c ijk phi I phi j phi k. And the reason, which was correctly remembered, is that the potential V of the actual physical scalars will be the sum on I of diw squared, which will then be quartic. So if I want a standard renormalizable theory in 4 dimensions, I'll stop my superpotential here. Okay, so let's try and figure out the classical approximation. So let's do some classical field theory right now, and let's try and study this theory in classical field theory and figure out what is the moduli space of vacua. So what should the moduli space be? I'll put this subscript classical to remind us that we're trying to do a classical approximation. Well, we have what kind of fields in our problem? So we've got the vector multiplet that has the gauge field and the gaugino. We're not talking about vector multiplets, so forget that I said that. We have the chiral multiplet, which has scalars and Weyl fermions. Weyl fermions don't get any expectation values. So we'll just have the space parameterized by these classical fields phi. So we'll have some phi fields subject to the constraint that the potential vanishes, which means that diw is 0. Now, if you remember in our superspace formalism, this potential came by integrating out something called an auxiliary field f. So one sometimes says that this is an f-term equation because fi is equal to diw, and we're setting it to 0. So one sometimes calls this a so-called f-term equation. Okay, so that's the answer. So let's do an example explicitly, just so you get a feeling. So 3 chirals. Let's call them x, y, and z. And let's take w is x, y, z. It's a kind of famous example. Okay, so what's the potential? It's a sum of quartic terms. And the minima are given by this formula. So m classical is equal to the locus where x equals y equals 0, or x equals z equals 0, or y equals z equals 0. So that's a pretty funny space. So if I think of each of x, y, and z as a complex line, it's like the 3 axes. So here's M, this space. And you should notice that it has an interesting singular point. So some general facts, some general observations. So the first is that these vacua are physically distinct. What do I mean by that? So if you're used to non-supersymmetric field theory, you're probably used to this case of seeing a space of vacua when you have spontaneous symmetry breaking. So you have some space whose tangent vectors are Goldstone bosons. And then no matter where you are on the space, the spectrum of particles is the same because they're related by the action of a spontaneously broken global symmetry. Here that's not the case. This classical space of vacua does not arise from spontaneously breaking any global symmetry. And we can see that the physics at different points on this manifold are different. So for instance, if we look at the place where x is not equal to 0, we could look at what the masses are for the y and z particles, and they depend on x. Right? So y and z are classically 0, so we'll avoid this. X has got Nevev, and we've got some masses for y and z, and they depend on what x is. A second observation, I highlighted this singularity. You see from this example that M is not even really a manifold. It has some interesting singular structure, some kind of branches, and in particular, the singularities in M are associated to new massless particles. So you see that in particular here, if we're living on the x branch where x is not equal 0, and we dial in towards x is 0 where we hit this singularity, the masses of y and z go to 0. So this is a very general feature. So in general, the effective field theory that we're talking about, that is the sigma model with target space M, breaks down at singularities. In M, and that's what's happening here. If we're just sitting along the x not equal to 0 branch, the only particle that we're talking about is the multiplet containing x. But when we dial into the singularity when x is 0, we better start talking about y and z as well. Okay, that was all in a classical approximation. We were doing some classical field theory, and now let's ask what actually happens in the quantum theory. So of course, in quantum field theory, couplings run. So if we have some Kähler potential in the UV, which we took actually to just be phi I, phi bar I, it may run under Rg to some new effective Kähler potential that depends on phi and phi bar in a more complicated way. And similarly, we might imagine that if we have some superpotential in the UV that depends on phi and some coupling constants, let me call them lambda I, that it runs to some effective superpotential that depends on these same degrees of freedom in a more complicated way. So what we're now going to prove we will now prove that in fact W effective is equal to W UV. However, I should emphasize K runs. So we won't be able to say anything about K without using more supersymmetry. So this kind of result, this fact that there's no Rg running in some quantity, is called a non-renormalization theorem. Okay, what are the key ideas in the proof? There are two. They are holomorphy and Spurion analysis. So let me elaborate on those. So first, holomorphy. So the UV superpotential, it depends, of course, on phi, the chiral fields, but also on some complex coupling constants, which I there denoted by lambda. Over here they were A, B, C. So it depends on some complex coupling constants. Now, notice the following fact. A constant, complex constant, is chiral. So if I think of lambda as a superfield, then d bar alpha dot lambda is 0. That's a trivial equation. So a constant is a chiral superfield. And so we could view, this very elementary observation tells us that we could view WUV as depending, as a, well, let's write it explicitly, phi and lambda, as a holomorphic function of phi and the couplings, where now I interpret, we view the lambda i's as some frozen background chiral superfields. So I imagine, what am I doing? I'm imagining an extended, bigger model where in addition to the chirals phi in my Lagrangian, I have some chirals lambda. Those chirals don't fluctuate for whatever reason. Their kinetic term has been turned off, and they're frozen in place. But it's my choice to think about this bigger model. It's completely consistent. Okay. Well, certainly if I'm considering this theory, it's not. It's not important that it is, though. Because we've imagined that we've fixed a theory at some scale with some effective superpotential at that scale, and we're just trying to lower the scale a little bit and see if anything changes. Yes? Yeah, so I'm imagining, so just like we had over here a moduli space of vacua where it was parameterized by some scalars. Those were the scalars, they were the bottom component of the chiral superfield. And here I'm thinking of lambda as the bottom component of a chiral superfield. So you could imagine embedding lambda into a superfield, and then you're looking at the special case where lambda happens to take a constant value. And only the scalar part of it is turned on. Okay, so we know that the superpotential is always required to be a holomorphic function of chiral fields. And so by promoting lambda to also be viewed as a chiral field, we can view W effective is a holomorphic function of phi and lambda I. So this is a crucial observation. So in other words, this equation must be true. So that's the first idea. So you view all the coupling constants in your problem, in your superpotential, as background expectation values for chiral superfields, and then you know just by the general property of holomorphy of superpotentials that the effective superpotential is also a holomorphic function of the couplings. That heavily constrains the way it can run. Okay. What about this comment about Spurion analysis? So this extended theory with phi's and lambdas may have some new symmetries. And I can use those symmetries to constrain the RG. So this is a maybe more familiar step. For instance, there's this famous example of doing this in the Stark effect, where you couple quantum mechanics to a background vector field E, but the fact that the electric field, and the fact that that electric field carries some definite quantum numbers under rotation allows you to constrain the kind of transitions between matrix elements that occur. This is something similar. So we assign some transformation properties under global symmetries to these lambdas, and the renormalization group flow has to be consistent with that assignment. Okay, so so these will be some global symmetries. So they're ordinary global symmetries. There are also R symmetries. So we didn't talk about the R symmetry in n equals 1. The U1R symmetry, we might need to use it in this kind of argument. So that's a symmetry under which the Q's transform as follows. So Q has charge 1, Q bar has charge, Q has charge minus 1, Q bar has charge 1, and that means that R of the superpotential, if you work it out, should be equal to 2. So I should stress that I don't need to assume that the underlying theory that I'm interested in has an R symmetry, just this extended symmetry, this extended theory where I think of the lambdas as fields. We'll see it automatically basically has an R symmetry, and we can use that to constrain the RG. Okay, so these are the two basic principles, holomorphy and Spurion analysis. And now let's actually do it in practice. So I'll do the simplest example on the board. So for example, a single chiral and we'll just take a cubic superpotential. So we'll have some mass term, m phi squared, plus some term that would ultimately give us a quartic coupling, lambda phi cubed. And we were interested in a renormalizable theory to start with, so let me start with that. None of this arguments actually depend on that. So this is our WUV. Now what are these symmetries that I was talking about? So we can single out two U1 symmetries. One is an ordinary U1, and the other is a U1R symmetry. Okay, so we'll make a little table. We're going to assign charges to phi, m, and lambda. Okay, let's just assign charge 1 to phi under both. Under this ordinary U1 global symmetry, the superpotential should be neutral. So in order to make this U1 a good symmetry, I will fix this to be minus 2 and fix this to be minus 3. In order for the U1R symmetry to be a good symmetry, I need W to have charge 2. So here I can put charge 0 and here charge minus 1. Okay, so the RG flow, the formula for W effective, must be consistent with these charge assignments. It must respect these symmetries.
Sorry. Why was it that R had charge?
Sorry?
Why was it that W has charge 2?
Okay, the question is, why does W have charge 2? Well, it's because this formula implies that d theta, if you like, should have R charge minus 1. So if I want to make something that's a Lagrangian that's in the end net R symmetry neutral, I need to start with a superpotential that has some R charge. Okay, so what can we say about W effective? So we know it is holomorphic, and we know that it should also have R charge 2 and be neutral under U1, this U1. So let's pull out m times phi squared. So m times phi squared, this combination has r equals 2 and u1 neutral. So we can write W effective as this times some function that we're going to try and constrain of neutral variables. We have 3 variables here and 2 constraints, so there's therefore 1 neutral variable. That neutral variable is phi lambda over m. So we know also that this is a holomorphic function. So this is the most general thing that we can conceive of that is consistent with holomorphy and this Spurion analysis. And now we'd like to constrain this function. Okay, so let's just imagine f is a general analytic function and expand it in a power series. So we have a sum over integers, some coefficients an, lambda to the n, phi to the n plus 2, over m to the n minus 1. So I've done nothing, I just expanded f. And now we have some more physics at our disposal. So we know something about various limits. So for instance, what happens when lambda goes to 0? What happens as a theory when lambda goes to 0? Yeah, it becomes free, right? So we turn off this, then the potential becomes quadratic. So that's a free theory. And so we know there shouldn't be any running there. We know that it should be well behaved in that limit. Let me say it that way. So if lambda goes to 0, the theory is free. So that means in this sum, I can't have anything bad happen when lambda goes to 0. So now that implies that n there is greater than or equal to 0. Okay. So we've gotten rid of half the terms here. How can we get rid of other terms? What's the bad thing about the other terms? The non-analytic in m. That also seems weird, right? So let's make that sharper. So if m goes to 0 and lambda goes to 0, and we can do this with m over lambda going to 0, then the theory becomes free. And we better have some reasonable expression. And so this implies, in fact, that n is less than or equal to 1. Okay, so we're basically done, because now what we've shown is that W effective, there's some coefficients, and we'll explain how to fix them. So it's equal to this. So what happened? I dropped the coefficients a there, and that's because the effective superpotential has to agree with the initial superpotential at tree level. So fix the coefficients at tree level. And of course, you'll recognize that this was the W that we started with. So that's sort of the way these arguments go. And okay, I did this for a single chiral, but you can easily extend it to a completely general Kähler sigma model involving n chirals, and just W any analytic function that you like. Just expand it in a series, and demand regularity and holomorphy, and you'll find that W effective is WUV. So in particular, it means that we have actually, although we started doing classical field theory of chiral multiplets, we've actually solved our quantum problem. Yes, question? A linear term in your superpotential. That doesn't matter. You just take another limit. The function will depend on two things. So you just do a general series expansion in both those variables. Completely general series expansion, and demand analyticity in all the free limits, and you'll easily find that WUV is W effective. It's a good exercise to do. I mean, maybe you'll convince yourself that it will work in general if you do a theory of one chiral but with an infinite series superpotential. And even that you can do just by this very simple analysis. Okay, so like I was saying, we've actually accomplished one of our big goals. So we were talking about renormalization group flows of n equals 1 quantum field theories. And we saw that if we could figure out what the moduli space was, we would know what the low energy theory was. And we were able to determine the moduli space in a classical approximation. But here, because of this non-renormalization theorem, we actually see that the classical moduli space for a theory of chirals is equal to the quantum moduli space as a complex manifold. So the locus of phi's where the F-term equations hold. And I stress here that this is only as a complex manifold. So the Kähler, although we were able to constrain the superpotential, the Kähler potential does renormalize. And so this is not these spaces are not equal metrically. So you only know them as complex manifolds to be equal. Okay, so what about theories with vector multiplets? So how should we embed those into a superfield? Well, I won't tell you much about how to do that, but I'll tell you a little. So what you should do is you should take a real superfield. I'll call it V. It's real, so V is V bar. That's got a lot of degrees of freedom in it, and we're going to impose a gauge invariance, a kind of superfield gauge invariance. So we impose that V can go under gauge transformation to V plus lambda bar, where this is a chiral superfield. So we impose this as this is a gauge redundancy. Right, yes, sorry, I'm going to be very telegraphic about the non-abelian case because I want to actually say something, but this is an abelian real gauge field. Right. Good. So this is a gauge redundancy. And okay, this, like I said, this V has lots of components. This lambda has lots of components, and so it's useful to kind of solve for most of that gauge redundancy, and we can actually do that. So if you fix most of the redundancy. I'll say what I mean by most. You end up with the following component expansion for V. So theta alpha, theta bar, alpha dot, sigma m, alpha, alpha dot. And I won't swear by the coefficients here. AM, this is an ordinary gauge field. Theta bar squared, theta alpha, lambda alpha. This is the photino or gaugino. Complex conjugate it, we get something like this. And then we have a top component. Okay, so we fix most of the gauge redundancy using this chiral superfield. We end up with this component expansion, and now all that's left is the usual gauge redundancy on A. Okay, so if you want to write an action, you need to not only have a gauge field, but you need to have an analog of the field strength. So let's introduce a field strength multiplet. So this will be W alpha, which can be expressed this way, d bar squared d alpha of V. So it has some essential features before I give you its component expansion. First of all, this is chiral. So if you hit d bar on this, you get 0 because you already put d bar squared here. Now, that makes it look like it could be a trivial chiral multiplet. Remember, we made this distinction between trivial and non-trivial chirals. Is this one trivial? Does anybody know? It looks like it's d bar squared exact. So is it therefore trivial? Well, the answer is no, because it's not d bar squared of anything gauge invariant. So V still has a lot of gauge freedom in it. So this is a non-trivial chiral. And we can do a component expansion. So as with all chiral multiplets, it's helpful to do an expansion in one of those shifted variables y that we introduced a couple lectures ago that soak up the chiral condition. So we have lambda alpha plus theta alpha d plus I f alpha beta theta beta plus theta squared theta squared, yeah. And then we have sigma m dm lambda bar alpha. All of these are functions of the y variable. So, okay, so another interesting feature of this chiral superfield is that it's fermionic. So its leading component is a Grassmann field. That's different than the other kinds of chiral superfields that we've introduced before. Okay, so I won't tell you at all how to do this in the non-abelian version, but I'll just say that in the non-abelian generalization, you end up with a W alpha again, which is chiral, and now in the adjoint, unsurprisingly, of the gauge group. So the component expansion of W looks very similar with all the fields in the adjoint. The main difference is just that I didn't tell you how to construct W from a V. That's a little bit more annoying. Okay, so since we've got this superfield analog of a field strength, we can write down a Lagrangian So let's write down our kinetic terms. Okay, so what is going on here? So first of all, we have integrated the square of w. I've written some non-abelian notation here, so we can have that in mind. The square of w, you can see that, for instance, you're going to get the square of f. So this is going to have the standard gauge kinetic term, and it will probably not surprise you by now that it will work out to have the standard fermion kinetic term as well. What is tau that appeared here? Tau is a complexifying gauge coupling. So theta over 2 pi in my universe plus 4 pi I over g squared. So it's a complexified version of the gauge coupling. And what I would like you to notice, and what might lead you to believe that indeed something interesting is going to happen, is that the kinetic terms for this gauge field look like a superpotential term. Right? They have been written as an integral only over half of superspace. So the thing that appears here has to be holomorphic. This is allowed because this is chiral. And that will enable us to constrain the renormalization group transformations of tau, the coupling. Okay, so just to make it even more clear, let me expand out some of the terms in that Lagrangian. So we're going to get a standard gauge kinetic term. We're going to get a theta term. We're going to get a kinetic term for the gaugino. And then we're going to get the auxiliary field squared. Okay, so this theory is called n equals 1 super Yang-Mills. And if the gauge group is G, let's we'll have gauge group G. So what is this really equal to? This is just Yang-Mills plus 1 Weil fermion in the adjoint representation. So that's n equals 1 super Yang-Mills. Okay, so let's try to constrain the RG running of this gauge coupling using holomorphy. Okay. The gauge coupling runs, of course, and what is the one loop formula? Let me write the one loop formula for you. So 1 over g squared, this is something that should be familiar to you if you've taken a quantum field theory course with non-abelian gauge fields. So at the scale mu, what should it look like? So there'll be some constant, it's sometimes called b naught, 8 pi squared log lambda over mu. That's the one loop solution for the RG. So lambda here is the strong coupling scale. And B naught controls the sign of B naught controls whether the theory is asymptotically free or infrared free, and which is which. So B naught positive is asymptotically free. So we have a theory with only one Weil fermion in the adjoint representation, And if you remember your kind of quadratic Casimirs and the factors of 11 and things like that that occur in these famous formulas, then you'll note that super Yang-Mills is indeed an asymptotically free theory. So B naught is positive. So we're in a situation where the coupling is very weak in the UV and runs to strong at some scale lambda. Okay. So it will also be interesting to notice something about the definition of this lambda. Okay. Let's note that if you write e to the minus 8 pi squared over g squared of mu. Okay. So first of all, just by manipulating that, that's lambda over mu to the b naught. But what else is this quantity? Why would we care about e to the minus 8 pi squared over g naught? Instantons, right. So this is the instanton action. This is the minimum action for an instanton. So if you want to think of running coupling, so you can view this as a definition of lambda, and we could try and reorganize the perturbation series in lambda just by using that definition. And perturbative corrections look like logarithms of lambda, but non-perturbative corrections look like power laws in lambda. Okay, so let's constrain tau here using holomorphy. Okay, so what will we do? Okay, so first let's write tau naught, or tau uv, is equal to b naught over 2 pi I. I'm just going to plug in that definition. Log lambda over mu naught, where now what have I done? So this was for g, this is for tau. So I've defined a complex scale lambda, which is now complex, is, so it's modulus of lambda. This is the ordinary strong coupling scale, the ordinary scale. That's what appeared in this formula, times a phase, which is e to the I theta over b naught. That's my definition of the complex scale. And the UV coupling constant is written that way. And we'll notice that this is looks like a locally holomorphic redefinition between tau and lambda. And so we'll think of everything as a function of lambda now. And that means that we'll have some holomorphy as a function of lambda, because the effective couplings must depend holomorphically on the UV couplings. So what did I just say? I said that tau effective, whatever it is, depends holomorphically on lambda. That complex scale lambda.
Sorry.
Yes.
But the complex of multiplets.
Yes. So we'll come to that. That will be essential momentarily. So tau also has some multi-valued property. And we just need to match the multi-valuedness between them. So if we shift theta to theta plus 2 pi, tau goes to tau plus 1. And that means that by definition lambda goes to e to the 2 pi I, lambda to the b naught goes to e to the 2 pi I lambda to the b naught. Notice that in my definition of lambda I have divided the phase by b naught here. So in order to take this into account, we can write tau effective at some scale mu should be b naught over 2 pi I log lambda over mu. That accounts for the shift, plus an arbitrary function that is single valued now, but holomorphic. To make it single values, I raise lambda over mu to the b naught, and then this makes it single valued. Okay, so just as so all I did here was use holomorphy and use the fact that we need this shift. And now we can do one more thing, which is that we can restrict the range of the sum. So n should be greater than 0 because lambda to 0 is a weak coupling limit. So by weak coupling, so we can say that this is n greater than 0. And lo and behold, we've actually proved a pretty strong result. So what did we prove? So we proved that, so this is actually the one loop RG formula that we started with. So, and you see that there's no other logarithmic terms here. So we proved that the perturbative running stops at one loop. However, instanton corrections, remember that this was the instanton action, and here we see it raised to the power n, so the term in the sum corresponding to n is the n instanton contribution. Instanton contributions are allowed. They're allowed, and they are in fact present. So I think, based on the outline that I saw, Ken and Trilligator may even tell you how to compute one, because it is important in Super QCD. Okay. Now, how far did we really get here? So in the case of the chiral multiplets, we were able to actually say that at least as a complex manifold, this equation was true. So the classical space of vacua was the quantum space of vacua. So we got pretty far. How powerful is this equation? Well, it's not that good because, the coupling still runs strong in the UV, or in the IR, excuse me. So the coupling still runs strong. So eventually, our formalism here will become strongly coupled, and we won't really know what to say. So this helps us for doing perturbative calculations, but it's not really a solution to super Yang-Mills in the same way that we had almost a solution to theories of chiral multiplets. So you here need a new idea. And I won't tell you how to use this new idea, but I'll tell you some interesting known results. So in particular, one thing you can do is you can compute the Witton index of this theory. So we talked about Witton indices, and famously Witton computed the Witton index of n equals 1 super Yang-Mills. So Witton showed that for SUN super Yang-Mills, trace minus 1 to the f e to the minus beta h is equal to n. So from our general discussion of indices, this means that SUSY is unbroken, and there are at least, but in fact by now it's known exactly, n vacua. And these vacua come about because the fermion condensate, trace W alpha becomes non-zero. So it gets a non-zero expectation value. And these n different vacui are labeled by different expectation values for this fermion condensate. Okay, so that's just a story, so you know some results. But next week I think you're going to hear about localization, and modern localization techniques make this kind of calculation bread and butter. Make it very easy. Okay? Finally, let me just tell you in the last few minutes some facts about theories with matter. So we've done pure chirals. We've talked about pure Yang-Mills a little bit. Now let's talk a little bit about super QCD. Yes, I'm using a supersymmetric renormalization scheme. So, I don't know if it has a different name than I guess it is different than the standard regularization scheme. Do you have something else in particular that you want everyone to hear?
Clear that this thing makes sense non-perturbatively?
That there exists non-perturbatively a supersymmetric scheme? Yes. That's a good question. So the question is, in deriving these kind of non-renormalization theorems, one assumes that you can work in a supersymmetric renormalization scheme. And the question was, do I really know that such a thing exists? I would have thought the answer is yes, because there's off-shell supersymmetry. So I can write down counterterms in superspace. And well, okay. Well, you see, I'm not sure the question matters that much, because the content of this formula was to say that the perturbative part stops at one loop. And surely you don't doubt that that scheme exists in perturbation theory.
If you just say that there is some effective action that controls the non-energy physics, that's certainly reasonable. But if you want to use the Wilsonian logic and integrate out shells of fields, then it's not obvious, especially in the gauge, source and gauge theory, that usually one way to do it is to do the cutoff on the Schrödinger parameter in the Feynman diagram. But that's perturbed. Not perturbed gauge and supersymmetry, that is perturbed.
Right. Okay, so indeed, I don't have a good argument saying that non-perturbatively such a scheme exists, but let me emphasize again that the main thing that we proved here is just a statement about where perturbation theory stops. And so that I think is robust.
How could you say that Suzy is still unbroken if we really promote tau to a spot field? Because in that case, derivative of the spot potential with tau is not vanishing.
No, but derivative with respect to tau bar is vanishing.
Yeah.
That,
But the spot potential is, like the absent potential is like a derivative of the spot potential in tau squared.
sorry, maybe I'm not understanding what you're saying.
Like if you promote the tau into a spot field, then there is an absent potential for tau. And if you take derivative in tau for the non-conductive spot potential, then you will not get any vanishing value for the absent potential.
Well, so that would require you to have trace W alpha to be non-zero, right? Which indeed is what I claimed happened here, but I didn't claim that that could be described in terms of the same UV effective field theory. Yes?
If I just think about running of tau as a complex Huffman constant, that doesn't look analytic. So, like if I write something like D depends on G, doesn't depend on feedback.
Only, well, but you do have some instanton actions here, right? So this perturbatively, but not, well, if you were doing, okay. If you discuss the instanton actions, you'll find that in general the long distance theta angle depends in an interesting way on the UV. That renormalizes also. If you just talk about the perturbative part, it's fixed.
Somehow we have to introduce lambda as a complex coupling constant, right? I mean, that's kind of obvious, what I'm going to say.
Yeah, that's what I did here. That was this formula.
I mean, if I just stared at the Lagrangian, there is one coupling constant tau. I mean, why do I have to?
Well, tau is complex, right?
Yeah, one complex coupling.
Yeah, and tau and lambda are essentially on equal footing here. One is just a redefinition of the other.
I mean, when you did the phi cube thing, you never introduced the lambda. Why do you introduce the lambda?
Well, if I wanted to, I could have taken the couplings in the superpotential and defined some new analytic functions of them and called them the new functions and tried to rewrite everything in terms of that. I could have done that. I just didn't do it. Maybe I'm not exactly understanding the spirit of the question. Okay. Okay, so very briefly, theories with matter, just so you can be prepared for what's coming. So now we'll have chirals in a representation R of our gauge group, and okay, you can find out how to exactly do the coupling between the vector superfield and the chiral superfield in many places. So what kind of things schematically will you find? You'll find some covariant kinetic terms. You'll of course find some Yukawa couplings and some scalar potential. So let me focus on the scalar potential, and I'll try and tell you what that is and what that looks like. So let's let T, A, I, J be matrices representing R. So what do I mean by that? So A here will be some adjoint index for G, and I, this one is the R index. So in the Lagrangian that you get when you couple chirals to vectors, you find the following term: dA phi bar I TA ij phi j. This is the D field that was in the vector multiplet. And these are the chiral scalars. Now remember that the Yang-Mills Lagrangian, I guess it's up here, still has a trace d squared term. So if we combine this with that term, we'll get a new contribution to the potential when we integrate out d. So what will it equal to? So V of phi bar. So we'll have the square of the F terms plus the square of the D terms. And we just need to evaluate what they are. So the F terms we know, that's the derivative of the superpotential squared. And now the D terms we can get from here. So we get this kind of term. So what can we say about the classical moduli space? So this is a sum of squares. So to find the solutions, we just set the components individually to 0. So it's a set of phi's such that f equals 0 and d equals 0. So this is 0, and phi bar I, ta, ij, phi j is also equal to 0. Now, I'm not quite done. The reason I'm not quite done is we're in a gauge theory. So we're only interested in gauge inequivalent vacua. We should quotient by the gauge group. So we should take these equations, the set of solutions, and we should mod out by the action of G. So this is the moduli space for a non-abelian gauge theory. In the classical approximation. Let me mention that there's one additional ingredient that one can include when your gauge group G has abelian factors. When your gauge group G has abelian factors, then you can write, so if G is U1, we can add to the Lagrangian an integral d squared theta bar d squared theta of d itself times some parameter kappa. This is called the Fi parameter. We can only do this when G is abelian, or when the part that we're focusing on is U1, because only then is D gauge invariant on its own. In that case, instead of setting this to 0, you set it equal to this kappa parameter. So then you get D from the matter sector. Well, so you get an equation like kappa. This is Ta phi. Well, T is just charges. Q phi bar phi. You get an equation like this, replacing the D-term equation. Okay, so this is a classical manifold. Now, very quickly, let me say that this quotient can be described alternatively in a very useful way. So here we have the F-term equations, the D-term equations, and the quotient by G. But it turns out that it's completely equivalent, although I don't exactly have time to say why, to say that it's the set of phi's subject to the F-term equations where we forget about the D-term equations and do a bigger quotient. So instead of quotienting just by G, we'll quotient by a complexified version of G. So the fact that these are equal is a kind of basic result in geometric invariant theory. And if we're in a non-abelian gauge theory where phi's are just valued in Cn, I think it's true even if there are no Fi pairs. Yes, but I think if you consider, for instance, say SUN super QCD, where we don't have any Fi parameters, I think it is still true. Yeah, and I think the reason is that I'm not trying to do the most general GIT quotient. I'm just trying to quotient on some very simple space. Okay, so we're basically out of time. So, okay, I invite you to spend some time, if you've never seen this, unpacking some examples. That's very useful. For instance, you could do some abelian gauge theory examples, and I'm sure Ken in Trilligator will tell you about this for super QCD soon. And so let me just tell you where this subject is headed. So in this discussion here, we're able to get the classical moduli space. But once we've introduced gauge fields, the running is not trivial. And typically, we hit some strong coupling in the IR. And we need a fundamentally new idea to figure out what the true quantum space of vacua is and to solve this RG problem. And that new idea is the idea of duality. So these kind of theories are solved, in the end, these moduli spaces are solved using Seiberg duality. And that will be discussed here, I think, in 2 weeks. So I'll stop here. Thanks. Yes, Greg?
Yeah, I just want to make a comment to students that what Clay is doing is an example of what I was saying is the symplectic quotient. Scalar manifold is symplectic.
Yeah.
The metric is invariant under G, is asymmetry. What he wrote there is the moment map. So that equation is the moment map equals 0 mod G. That's the symplectic.
Yeah, thank you. Yes?
If you couple gravity to your supersymmetric theory, is our symmetry promoted to some local symmetry, or is it broken down?
So, first of all, we're not in general discussing theories with R symmetry. So it's clearly not a general requirement that the supergravity multiplet contain a gauge field. There are quantum field theories without R symmetry that can be consistently coupled to gravity. Now maybe you ask, in theories with an R symmetry, is it a gauge field? And so I think the answer to that depends. So in the linear approximation it is, but whether that gauge field has standard kinetic terms or not depends on the very particular stress tensor multiplet that you're talking about in the particular supergravity theory. So for instance, I think in conformal supergravity theory, that ends up being auxiliary.
I see. So then, if we really want to study like the Holomorphy type thing in supergravity, we may not be in general saying that as there is some odd charge, we could constrain some of the fields, some of the superpotential.
Well, in supergravity you often have a bunch of low energy approximate symmetries, so I'm sure you can do similar things. Yeah. Okay, thank you.